Okay, so let me start by thanking the organizers. It's a great honor to be speaking at this conference. And it's the first time that I'm speaking in this room. The title of my talk is AKR and the laws of black hole mechanics. I will say a few things about laws of black hole mechanics and generalization to Rindler horizons. And in the generalization, the Raychaudhuri equations play a very important role, and that's the part that I want to emphasize. Okay, so this is the outline of my talk. I will set the scope and the context for this talk in the first 2-3 slides. Then I will give a slightly longer introduction. Then I will talk about the Rindler horizons and why we are interested in Rindler horizons. And then about the first law for Rindler horizons. So the thing that I want to bring forth here is that in 2003, there was a big confusion about whether there is a first law for Rindler horizon or not. And by a careful analysis of Raychaudhuri equation, we showed that there is indeed a non-trivial first law for Rindler horizon, and that's what I will talk about. For the experts, I have a couple of slides about some technical points, but I can skip those things. And then legacy of AKR. Okay, so we all know that the analogy between laws of black hole mechanics and thermodynamics has been deeply ingrained in theoretical physics for many years now. But the question that interests a lot of us is how general is the connection? In the following sense, we know that thermodynamics is applicable to all systems. You can apply to molecular motors in my body. You can apply to, the energy being coming out in this room when I'm speaking. So, the thermodynamics can be applied to almost all settings. The question is, can I apply the laws of black hole mechanics to a much more general setting? Can I apply it to a local region of space-time? Can I apply on observer-dependent horizons and things like those? So is there a notion of space-time thermodynamics, and how much can I get from the laws of black hole mechanics? So just to put things in context, let me just review the laws of black hole mechanics. I call this the black hole wisdom. So this is a full semester course on black hole physics summarized in one slide. Okay, so asymptotically flat black holes all have two killing isometries, partial T and partial phi. We study this in our courses. Black holes have famously no hair. They are all described by conserved charges. By carefully studying the linearized equations around black holes, we can come up with the laws of black hole mechanics. And these laws of black hole mechanics parallel thermodynamics. So there is a zeroth law of black hole mechanics which says that surface gravity on the black hole is constant. It does not change as you change generators. From generator to generator, it remains the same. And along the generator also, in time also, it remains the same. So constant temperature. First law of black hole mechanics says that change in the, if you throw a small, there are multiple versions of the first law. One version is that if you throw a small object into a black hole, then change in the mass of the black hole is related to the change in the area and the angular momentum of the black hole, like so. Second law of black hole mechanics says that change in the area is positive, which is closely related to the positivity of increase of entropy. Okay. An infalling observer crosses the horizon without anything special happening to the observer. So horizons are just normal regions of space-times, and asymptotically flat black holes are stable. Cosmic censorship protects us from naked singularities. Okay, so this is typically done in a full course, one semester course, but this is the summary. So the question is, how much of it can be applied to more general setups, Rindler horizons, and things like those. Okay, so although the laws of thermodynamics are well established for black hole horizons, Much less was said in support of the extension of these laws to more general settings, in particular the Rindler horizon. So in this talk, I will argue that laws of black hole mechanics, as well as some of their statistical mechanical interpretation, extends quite generally to Rindler horizons. This is in the context of an old paper I did, where we established the physical process version of the first law for Rindler horizon. And what we showed in that paper really was that there is a non-trivial first law for Rindler horizon, meaning there are actual physical processes that you can do, and the first law applies to such a setup. Okay. So this was the paper I did with Aaron Emsel, my good friend, and my supervisor, Don Marolf, in 2007. And this was really the first time that I did something technical with the Raychaudhuri equations. And since then, I mean, that was, as you will see towards the later part of the talk, this is quite a detailed analysis one has to do with the Raychaudhuri equations. Since then, I have given a number of lectures on various audiences on these wonderful equations. So it's an honor to give this talk at the AKR Centenary Conference. So after our paper and parallel developments by various other people, Raychaudhuri equations have become a sort of standard tool in string theory community, broadly said. In the earlier days, when I was a student, my supervisor used to joke that the knowledge of Raychaudhuri equation demarcates you from GR people and field theory people, but this is really not the case anymore. Raychaudhuri equations are everywhere. In fact, there are many people who understand the paper that I did with these authors much better than myself. I had a number of discussions on this paper with Paddy over the years, with Sudipta Sarkar, Sayantini Bhattacharya, and they have used such results in many different settings, especially in theories with higher derivative, curvature corrections in the context of generalized second law, and so on. Okay, so this is the plan of my talk. So I will present the status of the subject about the laws of Rindler horizon before our paper. And I will explain that there was a genuine confusion about this. And in this discussion, I will follow an article of Ted Jacobson. This article is called Horizon Entropy. And this article appeared in 2003. It gave a very concise review of the subject, very comprehensive and very clear review of the subject at the time. So I will closely follow that discussion. So unfortunately, Sudipta Sarkar could not come to this meeting, but I have prepared my talk such that it complements his talk. So Sudipta Sarkar will also talk about related things, unfortunately not. But there are many people in India who have worked on such things over the years. Sudipto, Sumanto, Sayantini Bhattacharya, Nile Kundu, just to name a few people. Okay, so slightly longer introduction now. So Jacob Bekenstein asked this question that can the second law of thermodynamics be violated by dumping entropy across the black hole, across a black hole horizon? I mean, if you throw something into a black hole, it disappears. What happens to the second law? And Bekenstein interpreted the horizon area as the measure of the missing information for an outside observer. And he came up with the idea of the generalized second law. So he introduced the generalized second law of thermodynamics, which says, which states that the sum of the black hole entropy plus the matter entropy outside the black hole never decreases. So GSL is a world in itself. I mean, there are many versions and many theorems. GSL holds even during quantum evaporation of black hole via Hawking radiation. The Hawking radiation has more entropy, and that way even the decrease in the horizon area is accommodated for in the GSL. And convincing arguments have been given which establish more generally that in any quasi-stationary process, the GSL will hold provided the ordinary second law holds for the matter. So the black hole part sort of comes as a consequence of these discussions. So these results truly imply that black holes are thermodynamic system and we should treat them as thermodynamic objects. So for more general horizons, Gibbons and Hawking in 1977 initiated this discussion, and they did this for de Sitter horizons. So let me just draw something on the blackboard. So the Penrose diagram of the relevant part of the Penrose diagram for de Sitter is like this. So one can apply laws of black hole horizons on such kind of horizon or on such kind of horizon or this one. So this was the sense in which it was like observer dependent. So when they did this paper, at that time, the corresponding generalization for Rindler horizon was much less accepted. But for de Sitter horizon, people did not seem to be like bothered. Like they agreed that, yeah, I mean, one can apply laws here, here, and here, but for Rindler horizon, there was some confusion. And it's important that we should generalize these laws of black hole mechanics to as generalized setting as possible, because the ultimate significance of black hole thermodynamics hangs on the generality it offers. And in the discussion, when you try to apply this to more and more general setting, in that discussion, the Raychaudhuri equations play a very important role, and hence it's an ideal topic to speak about here. Okay, so before I go into the technical things, so this is the currently accepted viewpoint in the literature. So the local entropy density of a horizon is indeed a valid concept, and this you can define for any horizon. And consequently, the laws of black hole thermodynamics extend quite generally to any causal horizon. Actually, in a few slides, I will give a technical definition for the causal horizon. So now one can ask the statistical mechanical question, what does this horizon entropy count? And the answer to this question is not settled. So this is where the literature stands at right now. Okay, so now I will say a few things about Rindler horizons. Okay, so in order to introduce you to Rindler horizons and the first law and so on, I need to go step by step. So the first technical definition I need to introduce is called causal horizons. Okay, so this is boundary of a past of any time-like curve. So like in de Sitter, you can have an observer which is reaching this point, and if you draw the boundary of this curve, this is this line. So this is this line here. You can consider an observer who is reaching time like infinity in asymptotically flat space-time, so the boundary will be like so. But this concept applies to all settings. Instead of having a diagram like this, you can have a diagram like this, where an observer reaches point P far in the future, and then the horizon would be this. And in anti-de Sitter also, you can have horizon. So this is a very general concept. Okay, so given this general concept, one can ask, now I can specialize to Rindler horizon. This is a slightly more restricted concept. So Rindler horizons have infinite cross sections. So these horizons, the way in the previous picture, these are like the cross sections are not non-compact. But in Rindler horizons, the cross sections are non-compact. So they are infinite cross-sectional area. And they are observer dependent as the other horizons, the one that I mentioned in the previous slide. So they are more restrictive also in the following sense. A causal horizon whose generators coincide with some killing flow are called killing horizons. And I will only work with I mean, I have to specialize, so I will work with these killing horizon. So the generator of the horizon is the horizon is generated by certain killing flow. Okay, so then the other important concept that I need to introduce is the so-called bifurcate killing horizon. So here the So there are two sort of horizon, and they intersect, and where they intersect, this is called the bifurcation surface. So a bifurcate killing horizon is a pair of killing horizons which intersect in a particular two-dimensional cross-section, so like so. So the Penrose diagrams that Sumanta was showing, or the Penrose diagrams that you have seen in your general relativity courses, they all have this kind of structure. Maximally extended black holes have this kind of structure. Okay, so at this point, relativists will cite a number of theorems, especially by Rax and Wald, and they will try to convince you that if you want to look at Rindler horizons, then it's better to work with bifurcate killing horizons, because many Rindler horizons can be thought of as bifurcate killing horizons. And indeed, this is what we also did. We were relativist, and this is the title of our paper. So no surprise in converting everything into bifurcate killing horizons. We did the same thing. So we converted, we were interested in questions about Rindler horizons, but then we looked at the bifurcate killing horizons. Okay, so before telling you about the first law, let me just say a few words about the second law, because second law is easier in this context. And it turns out, in fact, I don't have to say much, because Hawking's area theorem, if you have looked at the proof of the Hawking area theorem previously, then you know that the proof of the Hawking's area theorem is a local statement. It applies to any local patch of the horizon. So from there, it simply follows that the area of any bundle of the horizon generator is non-decreasing. So you don't have to do too much work. Just specializing yourself to a local bundle, you can argue that the area of the local patch of the horizon increases. Okay, so now in the Hawking's area theorem, there are a number of assumptions about positivity properties of the matter and things like those. So there are many variations, and hence there are many papers on this subject. But the essential idea is just this, that the proof of the Hawking area theorem can be made local, and hence so there is not much to say about the second law. Actually, second law is sort of easy. A lot more needs to be said about the first law, and this is what I will discuss next. Okay, so first law for causal horizon itself is a big topic, and one reason it is a big topic is because there are many versions of the first law. So I will only talk about one version, and that version is called the physical process version. Okay, so now let me say what is this and why we are interested in this. Okay, so this physical process version of the first law need to be contrasted with the stationary comparison version of the first law. So the stationary comparison version of the first law is about the comparison of two stationary solutions of the field equations. So you consider solutions with mass m and mass m plus delta m, and you ask how do I compare these two solutions, and that way you come up with the stationary comparison version of the first law. Okay, and this is properly formulated in the context of space of solutions of Einstein's equations, and best done in the modern language in the covariant phase space formalism of Iyer and Wald. So a more local version of the first law can be formulated when one inquires about the dynamical process by which the horizon area adjusts to a small flow of energy. So you have a black hole, you actually throw something into the black hole and then ask how the black hole settles. And this version of the first law was also discussed by Wald. I mean, this contrast between these two versions was brought forth by Wald in his book QFT in Curved Spacetime. And since this second version involves physical processes, it's called the physical process version of the first law. Okay, so the physical process version says that if you throw delta E amount of energy, then the change in the area, change in the entropy is delta S, which is delta E by T. Okay, so delta E is the energy flux across the horizon. And this version of the first law is established using the Raychaudhuri equation. So let me just briefly review this derivation, how this works. So there are only 3-4 steps that go into this. So first is the expansion, which Professor Sayankar gave the definition. So theta is the expansion of the horizon generators, which measures the fractional change of the area. So delta A is integral of theta over over the cross section of the horizon and the affine parameter along the horizon. So now the first trick is that you replace this theta with this funny combination. So you write theta to be d of d lambda of theta lambda, and then this second term. So the Raychaudhuri equations will tell you d theta by d lambda. So you substitute the Raychaudhuri equation in here. Raychaudhuri equations will have this RAB KB term. So now you substitute Einstein's equation into this, and you just follow this backwards, and you will see that essentially the first law is coming out. You make the assumptions that theta square terms is small, sigma square term is small, and if you just put this backward, you see that the first law is essentially coming out of this. Okay, so we essentially see that delta S is delta E by. Okay, so now so much so good, so far so good for the physical process first law of the black hole horizon, but there was a great confusion in from 2003 onwards, because 2003, like Ted Jacobson made this very precise. So I'm quoting this from his article, this horizon entropy article. So he says that the physical process version of the first law does not hold for any asymptotic Rindler horizons, since the nearly stationary conditions cannot be satisfied. And later in the paragraph he says the Raychaudhuri equations of course apply, but the terms neglected to arrive at the first law cannot be neglected. So he's referring to this theta square and sigma square terms. So we have to get rid of these theta square and sigma square term, and if those terms cannot be neglected, then the first law does not come out properly. Okay, so if we look at this paper and the discussion around this subject a bit more carefully, then we realize that this confusion was essentially fueled by an old calculation of Thorne, MacDonald, and Price, and so on, who considered a planet that falls in freely from infinity and crosses the Schwarzschild horizon. So the question they were interested in is, suppose you have a black hole of mass capital M, and a small object of mass small m falls into the black hole, then what is the condition in which the first law applies? So what they argued is that the process is nearly stationary. That is to say, the second order terms in the Raychaudhuri equations can be ignored. Theta square and sigma square terms can be ignored for the purposes of the first law, only if the object is sufficiently diffused. So what they said is that the object should be sufficiently diffuse, like gas or something. If the size of the object is much larger than square root m times capital M, then the conditions are met, and hence one can apply the first law. The confusion came because in order to take the Rindler limit, one has to take capital M going to infinity. So mass of the black hole you have to take very large in order to make it Rindler. And if you take the mass of the black hole to be very large, then it looks like the planet has to be very big, because R has to be much, much greater than square root m times m. So if you take m to infinity, then see the size of the planet has to be. And this was the conclusion that Ted Jacobson wrote, that m going to infinity is the Rindler limit, and this requires the planet to have infinite radius, hence the physical process version does not apply. Okay, so I hope I have explained the title of our paper. So what we showed is that there is a proper physical version for the Rindler horizon, and this is what I will explain next. Okay, so the main point of our paper was the following. So to make this law non-trivial, one must show that sufficiently quasi-stationary processes do in fact occur. That is the whole discussion. Because what Thorne, Price, and MacDonald showed is that when R is much, much greater than square root m times capital M, then one can ignore theta square and sigma square terms. And now For Rindler horizon, what one must show is that indeed sufficiently quasi-stationary processes do occur. In particular, what one must show is that processes exist for which the shear and the expansion remain small and no new generators are added to the horizon. So the Rindler horizon, theta and sigma remain small and some perturbation falls into the across the Rindler horizon. Okay, so via very careful and detailed analysis of Raychaudhuri equations and the properties of the bifurcate killing horizon, we showed that indeed such a thing can be done, and physical process first law for Rindler horizon makes sense. Okay, so I will tell you a bit of a story and then I will tell you a bit of the technical points. So when we wrote our paper, Ted Jacobson wrote to us, "Your paper gave me chills down the spine." He said that it's very interesting that the first law can be written in this way and the first law makes sense. Okay, so I was a PhD student at the time, and I must say that I did not understand the full impact of our result. And there was a lot of email exchange between Ted Jacobson and my supervisor, Don Marolf. But what I did was the Raychaudhuri equation analysis. In the appendix of our paper, there is a very detailed discussion of like exactly this kind of process. A small object passes through a Rindler horizon, and using Raychaudhuri equation, we argue that the physical process first law can be made to work. So in the long run, it's one of my best papers, and of course, I am very grateful to my supervisor and for involving me in this project, and also for the organizers for giving me this chance. So later on, Ted Jacobson and Padmanabhan and many others, they argued that the logic of our paper, in fact, can be turned around. And as I said earlier, several people understood my paper better than me, and I started doing something else. And what these people argued is that logic of the first law can be turned around to derive the Einstein's equation as an equation of state of space-time. So it is the local, I mean, the argument is a local Rindler argument and has been subject of many discussions and many conferences. There was a conference in honor of Paddy a couple of years ago, and there was a discussion of this. And this is really the context in which the subject of thermodynamics of space-time is being discussed currently. And all this essentially comes out of the Raychaudhuri equations. Okay, so now let me just give a few technical points on this discussion. So the first question is, what do we mean by sufficiently quasi-stationary? So what we mean is that the expansion and the shear along each generator are weak enough to neglect the second order term. And no new generators have to be added on the horizon. So it's no caustics and no shear and the expansion have to remain small. So the main issue that Ted Jacobson pointed out was whether sufficiently quasi-stationary processes exist or not. And these authors argued that they do not exist if R is much less than square root m times capital M. So the main, I mean, if you distill through this literature, then you find that the main worry was really the formation of caustics. So the formation of caustics causes two, okay, let me first explain the problem and then. Yeah, so here is the, like sort of the front view of the Rindler horizon. So infinite Rindler horizon, and some object is passing into this horizon at some location. So the worry was that there are these null generators, and these null generators will always converge at some point, and hence there will be a caustic. So this was the worry. And the formation of caustics caused two types of problems. One, in the region near the caustic, the expansion becomes minus infinity, becomes large. And also the caustics typically signal the addition of new generators to the horizon. So all of you have seen this diagram that when two black holes merge, then see, so this was the bigger black hole, a smaller black hole merged with the bigger black hole, then new generators are being added to to the horizon, and here, I mean, in this region, the expansion is very large. Okay, so the idea that R less than square root m times capital M is valid only. So the main idea was that this condition is valid when the object is to be thought of as so object is falling from infinity into the black hole. So the object began its fall from infinity, and that's how this capital M and small m were defined. The main issue that we pointed out is that this condition as written does not make sense in the context of Rindler horizon, and one should rewrite this condition in sort of covariant variables in terms of the killing energy of the object that is falling in terms of the surface gravity of the Rindler horizon. So this condition by itself does not admit a smooth limit to the Rindler horizon, and what admits the smooth limit is this condition. So one should write that condition as killing energy of the object and the surface gravity of the Rindler horizon. So first what we did is that we emphasized that the derivation of the physical process first law traces the generators of the horizon only back to the unperturbed past horizon. See, that was the reason why we worked with the bifurcate killing horizons. So even if these caustics form, if these caustics forms here, then you don't care, because they are behind the other bifurcate killing horizon. So object passes into the Rindler horizon here, and these generators start to converge, fine. And if these generators converge behind the past horizon, then you don't need to worry about the formation of the caustics. So this was the main point, that the derivation of the physical process first law only traces the generators back to the bifurcation surface, not beyond. And even if there are caustics beyond, we should not worry. And the second point was that one should characterize the condition in terms of the killing energy and the surface gravity of the Rindler horizon. So if you just apply these two things to Rindler horizon and carefully analyze the Raychaudhuri equation, you indeed see that the first law comes out. Okay, so this is all I wanted to say. So thank you, MSc. And in the abstract of the talk, I said I will say more about the second law, but perhaps another time. So AKR passed away in 2005, and the first time I visited Kolkata was in 2013. So we never met. And many times I wondered if he liked our paper, or like the appendix of our paper had a detailed discussion of Raychaudhuri equations and various technical issues about like perturbations falling into the Rindler horizon and so on. Whatever it is very clear that in any discussion about the notion of thermodynamics of space-times as presently understood, it all heavily relies on the details of the Raychaudhuri equations. So in that sense, his legacy lives on. And with this, I will stop and I will take questions now.
So thank you, Amitab, very much for the nice exposition of the application of Raychaudhuri equation in string theories as well. So we can take questions. We have enough time for that.
Yeah, Partho has. Yes.
Very nice talk, Amitabh.
Thank you.
But I had a question about your derivation, which you did not, of course, go into the details.
Yeah. Actually, I did not know about the preparation of the audience, so
that's perfect. I just had a question about the status of the zeroth law. Did you assume it, or did you prove it? Or?
No, the zeroth law is all about, so zeroth law has two main technical points. One is whether the surface gravity is independent of generators, like if you go from one generator to another, then kappa remains, and also in time, whether it remains. So once you convert Rindler horizons into bifurcate killing horizons, both these properties automatically hold, because if the horizons are generated by killing flow, then they have
the
constant surface gravity.
Thanks.
Yeah. Yes.
Hi, Amitab.
Yeah.
So my question is that when you talk about Rindler horizon,
Yeah.
so suppose this planet is falling, okay?
Yeah.
And then at every instant I can cook up some accelerated observer who will see a Rindler horizon near that planet, right?
Yeah.
So how is this condition
Yeah.
violated
So
there?
yeah, the question can be translated into some properties of the Rindler horizon. The key point is that the generator that generates the Rindler horizon is like this. And the killing energy is minus P dot chi, where chi is this, P dot chi. So P dot chi, if you carefully calculate, it depends on Z also. So that the question that you are asking can be converted into this Z. If you write it in terms of E chi over kappa, then although there is Z dependence, but it's written in an invariant way such that the condition is met. Yeah.
I have an elementary question.
Yeah.
Why is the Rindler horizon non-compact? I mean, cross sections are non-compact.
No. So no. So this requires a slightly longer discussion. One can consider a version of Rindler horizons where the cross sections are compact, but what we mean by bifurcate killing horizons are horizons which are generated by such killing flow. So such are non-compact.
The horizon is non-compact or cross-sectional areas are non-compact? What is the topology of horizon? R3?
R3, yeah. R3. So
Why
I
is
mean,
that?
it's literally this, like planes generated by null rays. Yeah. I can. Yeah, this is a bit of a technical. I can explain this later. Yeah. Yeah.
Hi Amitabh, just a couple of quick clarifications.
Yeah.
So the condition you wrote, this R much greater than
Yeah.
the geometric mean.
Yeah.
So that is tied to the points where the expansion or shear will dominate in the Raychaudhuri equation? Because you are able to express it in terms of kappa.
If these conditions are met,
Right.
then sigma remains small and theta remains small.
Okay. Because there was this work by Jacobson and Parentani where they tied kappa with the 2D geodesic expansion of the horizon.
Yeah.
So is that how theta appears in this condition? I mean, this condition, how is it tied to the expansion?
No, actually here what we are doing is that we are just looking at the geodesic congruence generating the Rindler horizon.
Right.
So that has theta and sigma. I mean,
Yeah.
those geodesics have theta and sigma. And then we are asking if you perturb this by some source of energy, TAB, which is satisfying this condition, then theta is small and sigma is small. It's just this.
Ah, okay.
Yeah.
Okay, thanks.
Jacobson Parentini came out later, a few years later.
Oh, I see. Okay.
2007, that paper came out.
Okay, yeah.
The sigma equation also admits sigma small, right?
Sorry?
The sigma equation, the sigma there is an equation, right?
Yeah.
The sigma equation will also admit, because sigma equal to 0 is not a solution of the sigma equation, right?
Yeah. So the main point was that for these, I mean, a bit more technically, so what enters into Raychaudhuri equation is the electric part of the wild tensor of the perturbing perturbation. And using that, one asks in what conditions sigma remains small, and that this condition comes out of that.
Sigma equation.
From the sigma equations, yeah. Omega equation doesn't, omega is always
equation is
zero.
zero, yeah. So
And-
from the sigma equation, you basically get
Yeah,
this condition.
from sigma equation we get this condition, yeah. So 2003 paper was in honor of Jacob Bekenstein.
Even his first paper on thermodynamics was
Yeah. 95, 96, yeah. In that paper was this logic reversing argument was there. Yeah, but at that time it was not known whether there is a non-trivial first law for Rindler horizons. And in 2003 he sort of distilled everything and said that no, it looks like there is no first law. And then we went it out.